Section 4.6, we're going to talk about three different equations, actually four. We're going to do doubling time for exponential growth, and then we're going to do a generic exponential growth. We're also going to do exponential decay, and we're going to use Newton's law of cooling. So we have four different formulas here. So just to just give you, a heads up that we are going to do four different types of equations. Now, it's not really necessary to do the doubling equation. We could have done this with our generic exponential growth, but the book goes over this formula here, so I'd like to do the same. Okay, so we have a doubling exponential growth here. So we have n of t equals n sub 0 times 2 to the t over a. All right, so n sub 0 is the initial population of whatever it is that happens to be growing. This is what the population starts with. N of t is the population after time t. Okay, 2 is because it's doubling. T is time, and a is the doubling time. Okay, so make sure your time increment and your doubling time are in the same units. So if one's in days and the other one's in months, we might have to convert days to months or months to days. But make sure T and A are in the same units of time. All right, so under ideal conditions, example number 1. Under ideal conditions, a certain bacteria population doubles every 3 hours. Initially, there are 1,000 bacteria in a colony, so find a model. So we're just plugging those numbers into our equation here. So initially, there's 1,000 bacteria, so that's what n sub 0 equals. And then the other number we know is that it doubles every 3 hours. So A is our doubling time. Okay, T is how much time has passed. So in general, A is not how much time it passed, but how much time it takes for the population to double. So if I plug that into this equation, I'm going to get 1,000 times 2 raised to the t over 3. Okay, so it is important that you don't multiply 1,000 times 2. Okay, 2 to the t over 3 is an exponential expression. 1,000 is the coefficient. So these don't get multiplied together. They're not like bases. They don't have like powers. Okay, so we're just going to leave it 1,000 times 2 to the t over 3. So question B says, how many bacteria in the colony after 15 hours? So if 15 hours have passed, it will have doubled 5 times. True? So 1,000 doubled to 2,000. 2,000 is going to double to 4,000. Right? So how many is going to be in this population if it's doubled basically 5 times over? All right? But what we're going to do is we're going to plug 15 into our function. So we're going to calculate the number of bacteria after 15 hours. So we're going to get 1,000 times 2, and for the t we're going to put a 15. 15 over 3, right? So 15 divided by 3 is 5, and that's where I got the doubling 5 times over. So we're going to multiply 1,000 times 2 to the 5th, which is 1,000 times 32, which is 32,000, right? So if a initial population of 1,000 doubles 5 times, we should have 32,000 bacteria, okay, after 15 hours. So if we have 32,000 after 15 hours, question C asks after how many hours will the bacteria reach 100,000? So this is our function value, and we want to figure out how long that would take. Okay, so pardon my really great whiteout skills here. All right, but we're going to set n of t equal to 100,000, and that's going to equal our equation 1,000 2 to the t over 3. Right? So we're just plugging 100,000 in for our population after time t. So we need to solve this for t. This is an exponential equation. And the t we're looking to solve for is up in the exponent. And the exponential expression is just 2 to the t over 3. The 1,000 is just a coefficient. So before we can bring this t over 3 down, we need to divide both sides by 1,000. All right, so if I cancel some zeros here, I get 100 equals 2 to the t over 3. Right? So now what we can do to solve this for t is to bring the t over 3 down. So I need to ln, excuse me, I need to ln both sides. And that'll allow me to bring the t over 3 out in front of ln. Now ln and 2 don't have like bases, so those aren't going to cancel. We're going to just get ln of 100 equals t over 3 times ln of 2. All right. So I want to solve this for t. So I think I'm going to multiply by 3 first to cancel the fraction. So I get 3 ln of 100 equals t ln of 2. And then to solve for t, I'm just going to divide both sides by ln of 2. And so I can plug that into the calculator, right? 3 ln of 100 divided by ln of 2. So I'm going to put the numerator in parentheses because there's more than one term, and then divide by ln of 2, and I get 19.9, almost 20 hours. Okay, so t is 19.9, and the units here are hours. Right, it's going to take approximately 20 hours for that bacteria count to reach 100,000. All right, so we have another doubling equation here. Okay, for rabbits. A certain breed of rabbit was introduced onto a small island 8 months ago. The current rabbit population on the island is estimated to be 4,100 and doubling every 3 months. All right, so what was the initial size of the rabbit population? Because they didn't say how many rabbits they put on this island. They just said it was introduced. Okay, so we know it grew to 4,100, and we know it's doubling every 3 months. Okay, and we know that it grew to 4,100 after 8 months. So the values we know, okay, we know the current population is 4,100. So that's n of t, right? What we don't know is n sub 0, how much we started off with, because that's what the question is asking for, right? How much time has elapsed? 8 months have elapsed. And how fast is this population doubling? Okay, that's our a value. And it is doubling every 3 months. So I'm going to plug those numbers into this equation. So now I get 4,100 equals n sub 0 times 2 to the 8/3, right? 8 over 3. So 2 to the 8/3 is a number that we can calculate. So I'm going to go ahead and do that. 2 raised to the 8/3 is this decimal 6.349604208. So in order to figure out n sub 0, I just need to divide both sides by 2 to the 8/3. So I guess I didn't really need that decimal right now. Let me go ahead and solve for n sub 0 by dividing by 2 to the 8/3. Right? So I'm going to divide both sides by 2 to the 8/3. Alright, so 2 to the 8/3 will cancel on the right, and that's going to give me my initial population. So let's divide 4,100 by 2 to the 8/3. and we get 645. Okay. So the initial population, they put 645 rabbits onto a small island, okay? And at the end of 8 months, they got 4,100 rabbits, all right? I think it's time to introduce some coyotes, all right? But this is how many rabbits were introduced to this island. So B asks, estimate the population 1 year after the rabbits were introduced on the island. So here's where we have, it's asking for years, and our doubling time is in months. So when we plug this number in there, we want to make sure we convert it to months. So 1 year is equivalent to 12 months, right? So we want to find not n of t, but rather n of 12, okay? So I'm going to take my equation, and I'm going to plug 12 in. Now, what is the equation? Because I guess I didn't really clarify that. Right, we have an equation now, since we know the initial population. We have n sub 0, which is 645 times 2 to the t over 3, okay? Because we have our initial population times the doubling t over 3, because it doubles every 3 months. So this is my initial, or my actual equation that we're going to use. So when we plug 12 into the equation, we want to make sure we use 645 for n sub 0 times 2. Now we have 12 months divided by 3. Okay. So after 12 months, it will have doubled 4 times. Everybody agree? So that's when we do 12 divided by 3, and we get that exponent of 4 here, that's doubling 4 times over. So we're going to get 645 times 2 to the 4th, and so we can just plug that into our calculator. All right, 645 times 2 to the 4th is 10,320. All right, so after 1 year, they have 10,000 rabbits. Okay, sketch a graph of the rabbit population. It's going to be exponential. Okay. So remember, we have this initial value of our exponential function, and so when time is 0, if I were to plug 0 in there, I get 2 to the 0, which is 1, and so this graph should start off with a y-intercept of 645, and then you should see it just growing exponentially. So plugging this into the calculator, I'll go ahead and let you work on that. All right, but just type this into your y1, okay? 645 times 2 to the t over 3. But it is important that you do not multiply 645 times 2, because that would be incorrect. All right, so next we're going to go over just a generic exponential growth equation, not necessarily doubling, okay? So we have somewhat of the same setup. We have a population after t time has elapsed. We have an initial population of e sub 0. Okay, we have an r, which is a relative growth rate. We can write that as a percentage if we need to, or sometimes they'll give it to us as a decimal, right? And then we have time. So this is just a generic growth, exponential growth equation. So let's look at setting up the first equation, right? The initial bacterium count in a culture is 500. A biologist makes a sample count of bacteria in the culture and finds that the relative rate of growth is 40% per hour, right? So this relative rate of growth, that's what we're going to use for R, right? Now 40%, I'm going to write it as a decimal, okay? So if I plug these numbers into this equation, I'm going to plug 500 in for n sub 0, and I'm going to plug in 0.4 in for R. So I get an equation, 500 times e to the 0.4t, right? The initial population, e to the growth rate times t. All right, so B asks, what's the estimated count after 10 hours? Right, that's just plugging 10 into the equation. So if I plug 10 into the equation, I get 500 times e to the 0.4 times 10, which I already calculated on this paper. But just to show you, e to the 0.4 times 10, we should get 27,299.07 bacteria. Okay, and then question C says, after how many hours will the bacteria count reach 80,000? So this is after some time has elapsed. So 80,000 is going to be our N of t value. So I'm going to take this equation and I'm going to set it equal to 80,000. All right, so here's my initial equation, set equal to 80,000. Right, and I want to solve this for t. I don't know how many hours it's going to take. So this is an exponential equation, and the exponential expression is e to the 0.4t. So I need to get this exponential expression by itself first. So the very first thing I need to do is divide both sides by 500. And so I'll get e to the 0.4t equals 80,000 divided by 500. Plugged into the calculator gets 160. Okay, so now what I can do is I can bring the 0.4t down, okay, or cancel this e. So the exponential expression, it's by itself. So I'm going to ln it at this point. And since the base here is e, it's just going to cancel. So I get ln of 160 equals 0.4t. And then to solve for t, I just need to divide both sides by 0.4. Right. So I'm going to get a t value, ln 160 divided by 0.4 is 12.68. Now this is time. Time should match the units of our growth rate. Okay, so the growth rate is 40% per hour, so this time is in hours. Right, so it's going to take approximately 12.687 hours to grow to 80,000. Right. Sketching a graph of the function again, it's just going to be an exponential function with a y-intercept of 500 because that's where the population is starting, and then it's just going to grow exponentially from that point. Next, we have a population of people example. So in 2000, the population of the world was 6.1 billion, and the relative rate of growth was 1.4% per year. It is claimed that a rate of 1% per year would make a significant difference in the total population in just a few decades. So they just want us to compare the population if the growth rate was 1.4% and if the population was 1%. So the equation, guys, is going to use the initial population, 6.1 billion, right? Because we're going from 2000 to 2050. So the initial population is in 2000. So we're going to use 6.1 for the population in 2000. And then if that's the initial population, that's when we're going to start the time. Okay, so that's why I wrote t equals 0 is the year 2000. So if we're looking for the year 2050, we're gonna use t equals 50 in there, right? So here is our generic exponential growth equation, right? N sub 0 e to the RT. So what we want to do is we want to plug our numbers in there. So we want to find the population in 2050. So we're going to plug 50 in there, right? Our initial population, e to the, now this 0.014 is 1.4% written as a decimal. Because remember, when you write it as a decimal, you bring the decimal point over. All right, so that's my rate, and this is my time. So plugging in all these numbers, if the growth rate is 1.4% in the year 2050, we'll have 12.28 billion people. So similarly, I'm going to use this equation, but I'm going to plug the growth rate 1% in there. Okay, so I'm going to plug 50 into the equation, but I'm going to use 0.01 instead of 0.014. And when we plug that into the calculator, we get 10.05 billion. So that very small decrease in population decreases the population by 2.28 billion people. And so that makes a big difference, right? So just utilizing this equation and knowing where to put the numbers is what you need to focus on. Right, so next we have an exponential decay. And the only difference between exponential decay and exponential growth is that the exponent is going to be negative. All right, so I'm going to write this bigger here. We have m of t equals the initial population times e to the negative r over t. Because our growth rate, we should be decaying. Okay, that means we need either a base that's a fraction or a negative exponent. So since we're still going to use e in here, we're going to opt for the negative exponent here. Right? So first example here, polonium-210 has a half-life of 140 days. So suppose a sample of this substance has a mass of 300 milligrams. Find a function of this form. Okay, so it didn't even talk about this form. It gave us this general exponential decay equation, and then it's giving us this basically a halving formula because it's using the base 2 with a negative exponent. Okay, so we're going to find two different equations here. Now, I'd like to explain to you what half-life is. All right, so say over here on the side, at time equals 0, say we had a population of 500, right? And say this population still had a half-life of 140 days. That means after 140 days, this population is going to cut in half. All right, so after 140 days, we're going to have 250 people. All right, so it's going to take another 140 days in order to half. So 140 days after the initial 140 days, that's 280 days later, the population is going to cut in half again. So it's going to go from 250 to 125. Okay, so if I keep adding 140 on this side, I'm going to keep halving this side. So 280 plus 140, 140 days later is 420 days after the initial time. And we're going to half this. So 125 halved is 62.5. So that's how half-life works. You wait for the whole amount of time to pass, and that's when the population is going to cut in half. All right? So going back to the question, if I were to utilize this equation, I have m sub 0 times 2 to the negative t over h. Right? So m sub 0 is our initial population, and h is our half-life. Right? And our half-life this time is 140 days. So if I plug those two numbers into the equation, that's going to give me the correct model. So we're going to get m sub 0 is 300 times 2 to the negative t divided by 140. Okay, this is the half-life model using base 2 here. Now, the next question says find a function, a model in this form. Right? So we're just going to plug the same numbers in. Right? So we have n sub 0. Now we have a negative RT, and I kind of blew over it, but R has a particular formula here. And so just in case you can't read it, R is ln of 2 divided by h, which happens to be the half-life. Okay, so I'm going to plug in 300 for the initial population. I'm going to plug in ln of 2 divided by 140 for the rate of decay. And I'm going to get an equation 300 e to the negative ln of 2 over 140 times t. Right? So it is important that the negative sign remain there. Okay. So let's go ahead and answer C. Find the mass remaining after 1 year. So again, we have a question asking for years, but our half-life is in days. So what we want to do is we want to make sure we convert 1 year to 365 days. So I can use either equation. It doesn't matter. I think I'm going to use the generalized one here though. Okay. So instead of m of t, we want to find the mass after 365 days. Right? And so the mass after 365 days, I'm just going to plug 365 in for t. So I'm going to get 300 e, raise that to the negative ln of 2 over 140, and then multiply that times 365. And that 365 is technically over 1 here. Right? So I know it's getting a little jumbled in there, but this is just something we can plug into the calculator. Right? So we're going to get 300 times e, and then I want to type in negative, let me not do a parentheses there, negative ln 2 divided by 140 times 365. Okay. Oops, can you see that? 300 e to the negative ln of 2 divided by 140 times 365. So it will do this in the correct order because we just do division and then multiplication in order from left to right, so it's going to calculate it correctly. And so I get 49.237. Now, does that make sense? Okay, after 365 days, right? So we kind of worked out some half-lives, and after 420 days, we had a population of 62.5. So 365 days. Ooh. Oh, I didn't. I started off with 500 here. I was thinking we had the wrong answer. But what if we started off with 300? Okay, let's make sure this makes sense. So at t equals 0, we had a population of 300. So 140 days later, we're going to have a population of 150. At 280 days later, we're going to have a population of 75. And then 420 days later, we're going to have a population of 37.5. So 365 days fits in between these two time periods, and our answer 49.237 fits in between our two population sizes. So this makes sense to me. All right, so 49.237, this is the mass, and the units of our mass is in milligrams. Okay. So after 1 year, we'll have 49.237 milligrams of this polonium. Right? Now, D asks, how long will it take for the sample to decay to a mass of 200 milligrams, right? So this is how much is going to be left, right? So after 200 is kind of in the first halving period, right? Because 200 fits between 300 and 150. So when we solve this, we should get a t-value less than 140. So what we're going to do is we're going to set our equation equal to 200. So we're going to get 200 equals 300 e to the negative ln of 2 over 140 times t here. So the exponential expression is here. The first thing we want to do is get rid of this constant. So I get 2/3 equals e to the negative ln of 2 over 140t. Right? So now I can cancel the e, so I'm going to ln both sides. So I get ln of 2/3 equals negative ln of 2 divided by 140t. So I'll go ahead and do this in a couple steps. I'm going to multiply by 140 to get rid of that fraction. All right, so the 140 will cancel on the right. So I have 140 ln of 2/3 equals negative ln of 2t. This is going up here. This is a mess. All right. Now, to solve for t, I'm going to divide by negative ln of 2. Okay, plugging all that into the calculator will get me what I need. All right, so I'm going to do that. So I'm going to do 140 ln 2/3. I'll go ahead and hit enter, and then divide that by negative ln 2. And I get 81.89, right? So t is our time interval, and our time interval is days. So it's going to take 81.89 days for 300 milligrams to decay to 200 milligrams. And that does make sense, okay? It fits our timeline we set here, right? Because 200 is in between here, and 81 days is between 0 and 140. So I believe we did it correctly here, okay, at that 81.89 days. Right, the graph is going to be an exponential decay with an initial population of 300. So you just kind of draw your decay, crossing the y-axis at 300. All right, that would be good enough there. So exponential growth, exponential decay, okay, exponential half-life, exponential doubling. Okay, those are all using the same types of equations. So we're going to look at a new equation now, right? And that is our Newton's law of cooling. And it's going to introduce some new variables, right? I really wish the calculator would have turned my screen yellow. But here it is. So here is our formula. So just in case you can't read this small script here, we have t of t equals t sub s plus d sub 0 e to the negative kt. Now this exponent is negative because we're cooling. The temperature is cooling, so it's like it's decaying, right? It's going to start off at a higher temperature than it's going to end up. So these variables, right? T sub s is the temperature of the surrounding, medium, it says. So this could represent the temperature of a refrigerator that you're putting it in. It could represent the temperature of the room you're placing it in, right? But that's the temperature of the surrounding, right? D sub 0 is the temperature difference, the initial temperature difference. Okay, so what is the temp difference between your object and the surrounding? Okay, and then we have K is a cooling constant depending on what the item is, whether it be a cup of coffee or a pizza. There's actually a known cooling constant for liver temperatures inside corpses, and so they would use this Newton's law of cooling to calculate time of death if you knew the right cooling constant for that liver, okay, inside a dead body. All right, kind of gruesome, and then T is time. Okay, so T of T is the temperature after time has elapsed. Then we're going to put our surrounding time in there, our temperature difference in there, and then we're going to look at what our cooling constant is. All right, so example 1, or actually the only example we're going to go over, says a cup of coffee has a temperature of 200 degrees Fahrenheit, and it's placed in a room temperature of 70 degrees Fahrenheit. So after 10 minutes, you wait 10 minutes, you check the temperature again, and now the coffee is 150 degrees Fahrenheit. And I think 150 is probably drinkable, right? But they want us to find a function that models the temperature of the coffee at time t. And so we know the temperature of the surrounding. We can calculate the temperature difference, but what we don't know is what the cooling constant of this cup of coffee is. So we're going to do a whole bunch of work here to find the cooling constant, because we absolutely need that in our equation. All right, the variables we need are t sub s, d sub 0, and k. Our function is with respect to t, so we can leave the t in there. All right, so the temperature, t sub s, the temperature of our surrounding is 70 degrees, because that's the temperature of the room that we're placing this cup of coffee. Right, the temperature difference, you put a cup of coffee that's 200 degrees in a 70-degree room, the difference between 270 is 130 degrees. All right, so we're just subtracting 270. So we don't know K, all right, but what we do know is after 10 minutes, the temperature is 150. So if I waited 10 minutes, I know the T of T is 150. So that's what I've written here, all right? After 10 minutes, the temperature is 150. So I'm going to plug all 4 of those numbers into this formula here, okay, this equation. So T of T is 150. The temperature of the surrounding is 70. Plus the temperature difference is 130. And then e to the negative k times t is 10. All right? So we knew the temperature of the surrounding and the temperature difference, and we knew after 10 minutes we get 150. So that's how we're getting this equation. And this equation has one variable in it, and that's k. And we need to solve this equation for k. So e to the negative k times 10, that's our exponential part. This exponential function has a coefficient, okay, and we're also adding 70 to this. Now it is important that you don't add 70 and 130 together, because they're not like terms, right? 130 has an e to the negative k t attached to it, and the 70 is just a constant. So the first thing we want to do is subtract 70 from both sides. And so we're going to get 80 equals 130 e to the negative k times 10, right? And then we're going to isolate our exponential expression. So now I'm going to divide by 130. So I get 8/13 equals e to the negative k times 10, right? So now I have the exponential expression by itself, so I can ln this. All right, so I get ln of 8/13 equals, ln and e will cancel, and I'm left with negative k times 10. So if I wanted to solve this for k, I'm just going to divide by negative 10. Right, that'll cancel the 10 and cancel the negative. So I'm going to plug this into the calculator. All right, I'm going to show you a trick too. So k is ln of 8/13 divided by negative 10, right? Now, it is important that we use all of these decimals, right? 0.0485507816. You don't want to round your cooling constant at all, right? My exposure here is wacky. All right, so I'm going to get 0.048550786. That's K, all right? So what I'm going to do in my calculator is, so that I don't have to type all these decimals for the remainder of the problem, I'm going to set K equal to this. Okay, so the way we do that is there's a store button, right? It's at the very bottom, right above the on button. It says stow. Okay, that's good. That will store your number to whatever letter you set it to. So I'm going to press stow. All right, and on the calculator it says answer arrow. Let's store that to the letter K. So K is above the parentheses, but it's in green. So I want to use the alpha key and then the K button here. And so I'm going to store this variable, K, to be this decimal. So enter, and it's going to say OK. But now, when you use K now, okay, for the remainder of this calculator's life, it's going to use that decimal. So you can keep storing over if you have more than one problem to do. But it really helps in plugging numbers into your calculator so that you don't have to type all 9 decimals here. All right. So in general, we have a function now for our temperature. Okay, it's going to be the temperature of the surrounding plus the temperature difference, e to the negative k times t. And I'm just going to leave the k there because I've stored k here. All right. So what's the temperature after 15? Well, I just need to plug 15 in for t. So I'm going to do 70 plus 130 e to the negative k times 15. All right. And so in my calculator, I'm going to type it just like this because I stored the cooling constant for k. So I'm going to do 70 plus 130 times e to the negative alpha k times 15. All right. And I get 132 degrees, 0.75, right? 132.75 degrees. All right, so after 15 minutes, 132.75 degrees. All right, so just finishing up this problem here on the back. After how long will the coffee have cooled to 100 degrees? So say 132 is still too hot for you. Okay, it needs to be 100 degrees for it not to burn the taste buds on your tongue, so you can actually taste food after drinking it. All right, so let's go ahead and take our temperature and set it equal to 100. So I'm going to do 100 equals our equation. All right, 70 plus 130 e to the negative kt. And solve this for t. So again, I have 130 being multiplied times our exponential and 70 being added to our exponential. So what we want to do is we want to subtract 70 first. All right, so I want to get 30 equals 130 e to the negative kt. Then divide by 130. So I get 3/13 equals e to the negative kt. And then I want to cancel the exponential, so I'm going to ln both sides. So I get ln of 3/13 equals negative kt. So I'm just going to divide by negative k here. All right. And then that's going to give me my t value. So ln 3/13 divided by negative alpha k is going to give me 30.202. Okay, so I will need to leave that coffee to cool for 30 minutes, right? If I want to drink it at 100 degrees. All right, so just to go over how to store that variable again, okay? So we found k ln of 8/13 divided by -10. So let me just do it again. So ln 8/13 divided by -10. That gave me my k value, right? So if you wanted to store that into your calculator, store is right here above the on, okay? So just press store. You don't need to do second or alpha or anything, okay? It's going to do alpha, or answer, with an arrow, and then we want to store the answer to the letter K, and letter K is above the parentheses in green, so we want to press alpha to get the K value of that button, so it's going to store that number to K. Right? So now if you were to press alpha K, anytime you press alpha K, it should pull that decimal back up for you. Right? It's a really nice hack there to not have to punch in 9 decimal places every single time you work a problem. Right? So that completes 4.6. All right, good luck, guys.